If you have a circle of radius 10, what's its curvature? It's an easy thing to remember. 1/10. What's fixed for a circle is its curvature is constant all the way around. The curvature of a circle is the reciprocal of its radius. So if you're prompted to, say, what is the curvature of a circle of radius 8? The curvature would be 1/8 or something. Okay. Or if it tells you have a circle whose curvature is 2/5, what's the radius of the circle? 5/2. So it's a reciprocal relationship either way. Radius to curvature for a circle is always its reciprocal. Okay.
And the unit for that would be meter, or like, I guess, whatever measurement it is to the -1?
No. Curvature.
Or is it unitless?
Curvature is dimensionless. Because if you look at the calculation, magnitude of a vector over magnitude of a vector, you really just have a dimensionless quantity. It's just a number that represents the twistiness of the curve at that point. Well, no, I take that back. If the radius of a circle is given in centimeters, what would the units for its curvature be?
Isn't it like radians per centimeters?
No, you're close though. I mean, think about it. The curvature is the reciprocal of the radius. If the radius is measured in centimeters,
1/centimeter.
yeah, 1/centimeter or per centimeter. So it's one of those weird reciprocal units that really doesn't have a numerator. It's not, kilograms per centimeter. It's just per centimeter because of the nature of finding its calculation. I don't mean to trivialize that, but I don't think she's as intense with units there. The most unit intense part is going to be the solving the differential equation where you have the acceleration given in centimeters per second squared. Make sure you keep those units for, and I say she as though she's going to be grading your test. I'm going to double check your units too. If your acceleration is given in meters per second squared, make sure the velocity is meters per second and the position is in meters. The other thing about units, there's some problems that are devoted just to the units for partial derivatives when you get to the 14.3 stuff. Some of the calculations are just, here's a function, find its partial derivatives, that's it. But some of them are tabular calculations based on, like the seawater problem she kind of did in class last week. There's a tabular problem on your review. Let's see. On this last page, next to last page. Yeah, right here. You're given some data here that represents wave height on the open sea as a function of the speed of the wind, I guess the speed of the wind moving close to the surface, and the length of time in hours that the wind has been blowing at that location. Okay, so these values here represent the height of the waves in feet. So this represents 4 feet. This over here is a V value representing the speed of the wind in knots. Wind speed. Oh, knots. Yeah, I knew knots were somewhere. Yeah. So this is representing 15 knots right here at this particular beginning of this row, and then up here this is time duration in hours. So she's got the units depicted on the table itself. So apparently, at a wind if you have a wind speed of 15 knots, and and it's been blowing that steadily for 10 hours, you get waves peaking at 4 feet above sea level. Okay, so that's the way you should interpret this. What would the units for, there's some estimations to do here, but what would the units for this be? dH over dV. And I'm saying d as though it's a regular Calc 1 derivative, but it's technically pronounced del H over, or del V. Partial of H with respect to V. What would its units be? Yeah, that's right. H's units are actually in feet. Be careful. Yeah, H, and use the Leibniz fraction here to let you know what the units are, because that's the handy thing about this particular version of partial derivative notation. The fraction here lets you know what units to use. So H's units, these are the H values, height in feet. So feet per V, wind speed in knots. So yeah, feet per knot. So who is being held constant here in this particular partial derivative? Time. So, at the 20, 20 is representing your V value, 10 represents your hour value. So you're steadily assuming, you're always dealing with a 10-hour duration constantly, and allowing your V value to vary in this particular partial derivative. Okay? So the units come from the fraction. If I wanted to estimate this, okay? Because you've got a table, it's kind of tricky to estimate. What you really need to do is to do a couple of averages and then maybe average your average. See, coming into the point v equals 20, t equals 10, right here, your wave height is 7. So if you have a steady speed of 20 knots for a duration of 10 hours, you get waves peaking at about 7 feet above sea level, okay? Now, if we want to approximate this, the rate of change of this height as the wind speed is increasing. So in other words, the increasing wind speeds are going this way. We want to essentially estimate this slope. Going from here to here, what is your change in height over change in speed? And then going from here to here, what is your corresponding change in height over change in speed? Doing a couple of, well, they're essentially secant slope calculations, okay? And then that'll be a couple of feet per knot calculations. Well, I want to crunch them out. Stupid. Nope, that sucks. There we go. Okay, so approximating partial of h with respect to wind speed at the 20 knot, 10 hour moment. So coming into that instant, and let me go and do this so I can actually drop everything on the board. Focusing on this point right here. We want to hold time constant. So keep time constant, and we want to figure out, as you're going in this direction, the reason I'm going in that direction is I want to measure increasing wind speed. Going from 15 to 20 knots, then 20 knots to 30 knots, what is the rate of change of the wave heights per knot? Okay? And so that's how you get a couple of secant slope calculations from it. So going from here to here, I want to approximate change in height over change in time. So I end up at a height of 7 feet, and I began at a height of 4 feet. So the change in height, 7 minus 4 feet, per the corresponding change in wind speed over here. 7 corresponds to 20 knots, 4 corresponds to 15 knots. So 7 corresponds to 20 knots, minus 4 feet corresponds to 15 knots. So coming into the point that I've got circled, the change in feet over change in knots is 3/5 feet per knots, or feet per knot, however you want to singularize it. Yes, sir. I pick up on things like raised eyebrows and wrinkled foreheads.
So you're looking at I guess the t values in the left column.
Yeah, the partial of h with respect to v will leave the other variable constant. If t is held constant, we're locating right there at the t equals 10 hour moment. Everything's going to be constant for t. There's no change in t measured with this partial derivative. Then when we switch to this one, who's held constant? V. So you pick your v value that's isolated there, 20, and now you're going to be measuring horizontally, because that's going to measure positive changes in time to look at the corresponding changes in height. Okay. So this measures dh over dv. Go in this direction, that measures dh over dt.
But you didn't do that for
No.
20 minus 15.
I did this like it's a pair of coordinates. At this location, a 7-foot height corresponds to a 20 knot speed.
Okay.
7 foot corresponds to 20 knots. A 4-foot height corresponds to a 15 knot speed. So I'm essentially finding the slope between these 2 points. I got that up top, so technically I need to say 20,7 and 15,4. The reason I'm not using time is because time is held constant. Time is constantly going to be 10 hours, so I'm not using the time variable at all. So I'm likening this to kind of like a secant slope from Calculus 1. Then that's just half the estimate. That's a partial estimate coming into the point that I've got circled. I also want to measure this average rate of change. So go from here to the next point outward and approximate your change in height over your change in time. So that's going to be, well, let me do the coordinate thing again. I'm still using the point 20,7. 20 knots corresponding to 7 feet above sea level. And I'm now including the new point 30,13. Because 30 knots produces, well, at that constant time value, 30 knot wind speed produces 13 foot crests. Okay, so then the change in height, 13 minus 7, over corresponding change in wind speed, 30 minus 20, in this case is 6 over 10, or, well, is it also 3/5? Is that 6 over 10? Okay, 3/5.
Makes it pretty easy.
Yeah. So you have an average, but see, notice that's kind of skewed. Your change in time here was, or your change in speed here was 5 knots, your change in there is 10 knots. But if that's the best you can do with this tabular data, 3/5 feet per knot coming in, 3/5 feet per knot coming out, the average of the average tells me it's approximately 3/5, so 0.6. So that means at this instant, your wave crests are changing at about 0.6 feet for every knot of wind speed you increase. Okay, feet per knot. So then if you're prompted to approximate this one, the partial of h with respect to t is going to leave v constant. So pick your v value. This is v, this is t. V value is going to be 20. Now I'm going to be going this way. And I'd say, estimate this increase. There's a 2-foot increase for a 5-hour duration coming into that point. And then there's a 1-foot increase for this 5-hour duration. Okay, so you have this average is 2 feet per 5 hours, so 0.4 feet per hour, and then 1 foot per 5 hours, so 0.2 feet per hour there. And then average those two averages to get a rough idea of what that would be. Ish. Okay. Let me pause for a second. I don't mean to tease you, but I've got a copy of your test book. And I'm not teaching, I keep wanting to say this, I'm not teaching from the test. I just want to make sure everything here is confidently ingrained in your brain, so you'll know what to expect. Okay.
Thank you.
Okay, so just going over the rudiments of the test. Okay, she's kind of jumbled up the order a little bit because the first two problems are some partial derivatives. Just good old find the partial derivative of this function. Find partial of z with respect to y. Find second partial of z with respect to xy. And so remember what the notation stands for here. In this second partial derivative, what's important about that del x del y in the bottom when you do partial derivatives?
You have to do both, but you have to do, I guess it doesn't matter which one.
But they can't be done simultaneously. They have to be done sequentially.
Right.
So if I want to eventually get this, what first partial do I have to take? First partial with respect to x, because it's the first one listed. Then when I've done the first partial with respect to x, I want to take its partial with respect to y. Okay? So there's this notation. There's this notation. Or sometimes it's capital F. And sometimes it looks like this. What does that stand for? Second partial with respect to y means do your first partial with y, and then when you have it, then do its partial again with respect to y. Okay? So there's really four second partials you could be asked to do. You could be asked to do second partial with x, so first x, then its partial with x. You could be asked to do this one, first partial x, second partial y, or first partial y, second partial x. But what's one thing Beth told you about these two? That you can always reliably count on for this class. They should always be the same. For this class, yeah, we use the same function notation. Those will always equate to each other. Those mixed second partials should always be the same. And that'll be a fact we kind of want to remember later on in this course. It'll kind of come in handy when we deal with conservative vector fields and such. Okay? So yeah, your first problems are just finding some partial derivatives, okay? How would you there? How would you do this? Given a vector function, be able to find the parametric equation to its tangent line at a specific point. So, given a vector function, and tracer. I'm terrible for abbreviating, but I'm verbalizing it. Hopefully you'll know what I'm saying it for. Find the parametric tangent line equations at, let's say t equals 0. Be straightforward. Okay. How would you go about doing that? What are the two things you need to find the parametric equations for any line, regardless of the context? You need a derivative. Well, before you get to that, just the two rudiments of finding the parametric equations for any line.
Do you need the magnitude?
Well, you need so you're suggesting I need a
Unit vector?
vector, any vector. Doesn't have to be a unit vector. I need a direction,
Okay.
which likens to slope. And what's the other essential thing for finding any equation of a line? Parametric 2D.
Parameters?
Okay, location specifically. In other words, I need to know a point on the graph. I need to know a point on the line and a direction vector. Those are the two rudiments for finding the equations of any line. So once you know a point and you know the vector, you go into the parametric equation format. Let's say A, B, C is your well, no, actually the standard's usually this. X sub 0, Y sub 0, Z sub 0 is your point. And let's say your direction vector is AI, B, J, C, K. What do those vector components become in the line's equations?
I, J, and K?
Well, no, you don't use I's, J's, and K's here. You take the I, J, K component of the direction vector, and what does it do here? Did you use the parameter t in any way, shape, or form?
Yeah.
It becomes what for t?
The constant.
The coefficients, yeah. So, the coefficients of t from that direction vector, all right? So, how do I get a point from this? What's the point going to be from this vector curve? I'm at t equals 0. So, how do I get the point? Plug it in, yeah. R of 0 gives me the vector 0, comma, 2, comma, 1. Now it's a vector, but what's the point that I should be considering? No. Keep in mind what this stands for. This is a position vector. It is tailed at the origin. The head of the vector with those components is located at the t equals 0 point on the curve. So basically translate that into this point. So there's part of what I need. I've got half the answer right there. If I'm supposed to be tangent to that point, I know these parametric equations should use 0, 2, and 1 because that's the location where I'm at. Now I need the components of the direction vector. If I want the direction that's tangent to this curve at t equals 0,
Then you just take your derivative of
first
your
derivative.
vector.
So I need r prime, 2t, -1, and 2e to the 2t. And how do I get my direction vector from this?
T equals 0?
Yeah, plug in t equals 0. Because t equals 0 was the location given in the problem. You plug it in here to get your point location. You plug t equals 0 into r prime to get your tangent vector location, or direction.
You go r prime of 0.
So r prime of 0, thank you, yeah. That's going to be 0I, negative 1j, 2e to the 0, so 2k. So that's the direction I should be heading from this point on this curve. All right? So what role do those numbers play in my answer? Those are your t coefficients in x, y, z, a, b, c order. You have a 0 for your coefficient here, so no need to write that. You have negative 1 for your coefficient there, and you have positive 2 for your coefficient there. That's where your point always falls in the parametric equations for a line, and that's where your direction vector components always fall in parametric equations. Okay? The context here is a tangent vector. So, in other words, if this path, whatever it looks like, if it's some kind of, spiral out in space or something like that, at t equals 0, we'll say it's right here, if you're going in this direction, that vector represents essentially the direction of your headlights. Okay, because your headlights are always going to be pointing straight. Okay, so your tangent vector is always going to be going like this. So this line would look something like that, tangent to that curve at the t equals 0 timestamp. Does Beth not make you talk as much?
No.
No? Is that going to be an adjustment? I want you to be comfortable. I want you to be very comfortable in this class because I'm obviously a very informal teacher. So but
It helps.
so yeah, just feel free if you have any questions or any kind of interjections, just let me know. And any what ifs or how the hex. Okay. So parametric equations for parametric tangent line equations are going to be essential.
I got a question about the notation for partial derivatives.
Yes.
On our review, there was a, I guess it had dx in there, and I was confused. It's on the last page.
On the very last page, yeah, right here.
The E and the G. Yeah, there.
Oh, so this E and this G.
Well, E and G at the bottom.
Oh, so okay, so just finding the partial derivatives. Okay,
But
so this one, it's a second partial, and the order here means find your first partial with respect to y,
and
then take its partial with respect to x.
Is there any way we can
Why-
work through one of
Let's
those?
do this one, yeah.
Okay.
Thank you.
I mean, I want to devote the first half of class, so we got about 5 minutes left to kind of going over the review rudiments, and then go ahead and start into the beginning of Test 3's material. Okay, so on E here, and I do have the solutions posted. The solutions to the review are posted on D2L. The work to the solutions are not, but just the answers are there. So if you want to at least double check your answers, you can. But feel free to email me if you want to see a little bit more, or bring it up in class on Tuesday or Thursday. So on E here, you have to do the first partial with respect to y. So I'm going to go ahead and call this f of xy is natural log of 3x squared y to the fifth plus 1. I think this one kind of involves some, I don't want to say intense calculation. You just have to keep in mind, whenever you're doing a partial derivative, one variable stays constant, the other one is your variable you're focusing on. So the first partial I have to do here is the partial with respect to y. So partial with respect to y, and mine look like little number 2's, but that's just my sloppy, I guess, notation for partial derivatives. So the first partial is done with y. I'm going to leave x constant and only focus on y. So the outer function here is a natural log. Natural log makes me do 1 over the argument. That's the derivative for natural logarithm. And then times, so instead of putting 1 up here, I'm going to put my chain rule multiple on the top. The inner derivative here needs to be done with respect to y. So if I'm treating x as a constant, there's a function of y right here. 3x squared is going to be like a coefficient. And then I want to do the derivative for y to the fifth with power rule. So 3x squared's there times 5y to the fourth. So that should properly become 15x squared y to the fourth, and your plus 1 vanishes. Okay? So there's my first partial of this function with respect to y. True, maybe? Okay. So then to finish the partial that I'm prompted for here in part E, I want to now take its partial with respect to x. So we're doing the second partial. First was done with y, now this one's going to be done with x. So now I have two functions of x showing up, a numerator and denominator. So I just go ahead and suck it up. You got to do the quotient rule. Okay? Just keep in mind, now we're switching roles. X goes to being our variable and y goes to being a constant. So the quotient rule is you do the top derivative times the bottom left alone. So I'm going to give myself plenty of room here. The derivative of the top with respect to x, 15 is a coefficient, x squared becomes 2x, and then y to the fourth stays y to the fourth. So essentially the 15 and the y to the fourth are coefficient constants. And that would give me 30x y to the fourth times the bottom left alone. Okay, so there's the first half of the quotient rule, or at least the numerator half of it. And then minus, leave the top alone. So that's the f prime g, here's the f g prime part of the quotient rule. And if I've said product rule, that's a mistake. I mean to say quotient rule, because obviously it's a quotient. So top left alone times the derivative of the bottom with respect to x. So again, y is treated as a constant. 3 and y to the fifth here are coefficients, and x squared once again becomes 2x. So that should become 6x y to the fifth, and the plus 1 goes to 0 there as well, because this is a standalone additive constant. All over your denominator squared, which I think I would just leave this as a group squared like this, as opposed to actually forming it out. I did that in the intro. The only thing left to do is just to sort of double check. You'd be surprised with these partial derivatives. You actually get some weird like terms showing up top that can make it reduce a little bit better. See, like if I actually hash out this numerator, that multiplies out. This is monomial, this is binomial, so that's going to become 90 x to the third, y to the ninth first. Then my plus sign, 1 times this would just be another copy of 30xy to the fourth. And then minus, this is mono times mono, so that's going to be 60 plus 30 is 90, x to the third, y to the ninth. So see, you do get a pair of like terms, and they're the sweetest like terms of all. They're opposites of each other, all over your denominator squared. So my proper statement of the second partial of f mixed with y then x is a numerator of 30xy to the fourth over my original denominator. Wait a minute. No, I did that right. Sorry, brain fart, but I'm better. That should be your final partial yx order. Do you see what happened? Maybe?
So it was just a typo on the sheet.
So there's a typo on the sheet?
It said dx and not the partial derivative symbol. That's what was throwing me. I thought,
Oh, okay. Oh, this right here.
yeah.
Okay, that means you're going to be doing the second partial. So that's an operator notation. Essentially, it comes from this. You take your function, you do its first partial with respect to y. And so that means the operation of taking first partial with respect to y for this. And then you want to take this partial with respect to x. Even though it's kind of backwards written right here, whenever you finally bring this together, the del operating on del is what gives you a del squared. And then the order here, you have to go from right to left. The first partial was done with y, the second partial was done with x. And so that's why that exponent is there. It's not really a typo, it's just saying,
The bottom, the denominator is a d.
oh, the d, oh yeah, that is a typo, sorry.
That's what
So, 7 minutes later, sorry. You didn't even need to see that, did you? You didn't even need to see that. Okay, sorry. I just go straight for what I thought was the question. And you also mentioned something about G, the same
Well,
typo.
the same thing.
Okay, so same typo. That should not be an Arabic D, that should be sort of that del backwards 6. Yeah, so that's just a typo.
Do you have a moment to go through a level curve?
A level curve problem. Okay, a very quick moment.
Quick.
Well, actually, we're kind of going through some level curve stuff tonight. But if it's one that you had to draw, let's see, if you had to sketch some level curves. So something like, the function f of xy equals 9 minus x squared minus y squared. And see, the textbook uses C, I think. So let me try to be consistent there. They say use the C values of, I don't know, 0, 5, and 8. Okay, just picking that. So those are actually the Z values that I'm looking to slice into this curve with to produce that particular topographic projection, or level curve projection on 2 dimensions. So you take your curve here, or you take your surface here, and the Z variable is the f of xy symbol. And for each of these little values you're given here, just set f equal to those. If I set it equal to 0, what's special about a Z value of 0? Where does that locate you in space?
The origin.
Well, not just the origin, think three-dimensionally. If I'm in 3 space, and I'm at the places where Z is entirely 0, what's special about that location? The xy plane. Yeah, not just the origin, not just a point, but you're at every point on the xy plane. So in other words, whatever this surface looks like, when it hits the xy plane is what this will produce. So, and when I set that equal to 0, it should turn into a relatively familiar 2-dimensional curve. Instead of solving this for x or y, solve it for x squared plus y squared because of this. That x squared plus y squared, expression pops up a good bit in this class when you're dealing with multivariable functions. If I solve it for x squared plus y squared, it turns into x squared plus y squared equals 9. So what kind of curve would that produce in the xy plane? A circle, centered at the origin with a radius of 3, yeah. So if I had to overlap all these level curves, I would just simply draw a circle of radius 3 as best as I could freehand. And maybe, give me some indication that you know that does represent a circle of radius 3. And also, if we're thinking of this as like a topographic map, it's probably best somewhere along the curve to remind me that that's the z equals 0 level. So when this surface hits the xy plane, it produces that particular curve of intersection. And we're going to higher values of z. We're going to z equals 5 next. So if you do the same process, if you solve this for x squared plus y squared, bring that whole quantity over, and then subtract the 5 from the 9. So going from a height of 0 to a height of 5 produces this level curve. So now you're still dealing with a circle. So apparently every level, is it too bold to say that every level curve for this function is going to be a circle? Yeah, that's a true assertion because you're always going to have this x squared plus y squared expression you solve for. In this case, going 5 clicks higher, you get a circle with radius 2. So I'll try my best to freehand that. And again, those are intercepts of 2, and that represents the z equals 5 level. Does that give you an idea of what this surface kind of looks like? As you kind of go from the origin, or go toward the origin, the topography is getting, okay, at the xy plane, you have this curve of intersection, circle of radius 3, and then 5 clicks higher, I get a circle of radius 2, so that kind of gives you at least a cone shape, okay? And then when I get to the value z equals 8,